Last chapter we filled the instance with memory. But memory doesn't manage itself. Something has to move data between that memory and the disk, and something has to clean up when things go wrong. That's the job of the background processes. Small programs that start with the instance and never stop running. Here's why this chapter matters. Naming the core background processes and saying what each one does is one of the most classic opening interview questions there is. You will get asked this. So let's learn the 5 essentials cold, plus a 6th worth mentioning. And I'll give you a single paragraph that answers the whole question. Here's the idea. When an instance starts, Oracle quietly launches a whole set of these small always running programs. Each has one narrow job, and working together they keep the database healthy on their own. No user ever has to request it. The analogy I like is a building's maintenance crew. One person runs the boiler, one keeps the logbook up to date, one takes out the trash. You are not expected to recite every process Oracle runs. There are dozens. But a senior candidate should be able to comfortably explain the 5 I'm about to walk through and know the reason each one exists. Here's your roster. 5 names, 5 one-line jobs. DBWn, the database writer, writes dirty blocks from the buffer cache out to the data files. LGWR, the log writer, writes redo to the log files, and crucially, it does that at commit time. CKPT, the checkpoint process, records checkpoints into the control files and data file headers. SMON, the system monitor, performs instance recovery when the database starts up after a crash, and PMON, the process monitor, cleans up after failed user sessions. Memorize these 5 as a set. We'll now take each one and go one level deeper, because knowing the name isn't enough, you have to know why it's there. First, DBWn, the database writer. Its job is to take the modified data blocks, we call them dirty blocks, sitting in the buffer cache, and write them out to the data files on disk. Here's the clever part, and it's worth stating in an interview. DBWn writes in the background and in batches. It does not write on every single change. That's the whole reason your transactions feel fast. You modify data in quick memory, and DBWn quietly syncs those changes down to slow disk later, in efficient batches, completely out of your way. If DBWn had to flush to disk on every change, the database would crawl. Second, LGWR, the log writer, and this is the special one. It writes the redo entries from the redo log buffer out to the online redo log files. What makes it different from DBWn is the timing. LGWR writes at commit time. When you commit a transaction, LGWR flushes that redo to disk before the commit actually returns to you. And that single behavior is what guarantees your committed change survives a crash. So here's a trap interviewers love. What makes a commit durable? The answer isn't the data files. DBWn might not have written those yet. It's LGWR writing the redo to disk before the commit returns. Lock that in. It connects directly to redo and archiving in Chapter 10. Third, CKPT, the checkpoint process. Its job is bookkeeping for recovery. Periodically, Oracle takes a checkpoint, which is essentially a known good line in the sand, and CKPT updates the control files and the data file headers to record that it happened. Why does that matter? Because it marks how far back recovery would need to go. Without checkpoints, recovering after a crash might mean replaying an enormous amount of redo. With them, Oracle knows it only has to go back to the last checkpoint. CKPT also signals DBWn to write and keeps all that recovery bookkeeping consistent. Think of CKPT as the process that keeps memory and disk honest about where they stand. Fourth, SMON, the system monitor. This is the hero after a crash. If the instance died suddenly, a power loss, an abort, there was probably uncommitted work sitting in memory, and the data files were left in an inconsistent state. When the database next starts, SMON automatically performs instance recovery. It replays the necessary redo and rolls back any uncommitted transactions until the database is consistent again. And it does all of that with no human intervention. SMON also handles quieter housekeeping, like coalescing free space. So if someone asks what happens when you restart after a crash, the name you want in your mouth is SMON. It's the automatic recovery process, and it connects right back to Chapter 5's startup stages. Fifth, PMON, the process monitor. Sessions don't always disconnect politely. A client crashes, a laptop lid slams shut, the network drops, and now there's a dead session still holding locks and resources. PMON is the cleanup crew for exactly that. When a user process fails, PMON releases its locks and frees its resources so the rest of the database isn't stuck waiting on a session that's never coming back. One honest modern footnote. In recent versions, this role is spread across a small family of processes rather than a single PMON. But in an interview, naming PMON and clearly stating its job, cleaning up failed sessions, is precisely what they want to hear. There's a sixth process worth mentioning, because it's the bridge to everything in the backup world, ARCn, the archiver. When a redo log group fills up and Oracle switches to the next one, that filled log would normally just be overwritten later as the log cycle. But if the database is running in archivalog mode, ARCn steps in and copies the filled redo log to a separate archive location first, often the fast recovery area. Why care? Because those archived logs are what let you recover a database forward in time and take hot backups while the database is running. ARCn is the hinge that connects the redo logs in Chapter 10 to the ARCn backup strategy in Chapter 14. No archiver, no real recovery. Here's the slide to rehearse until it's automatic. When they ask you to name the background processes, you want this whole paragraph to come out in one smooth breath. Listen, DBWn writes dirty blocks to the data files. LGWR writes redo at commit, so committed data is durable. CKPT records checkpoints in the control file. SMON does instance recovery on startup, and PMON cleans up failed sessions. Then the bonus, ARCn archives the redo logs when we run in archivalog mode. That single paragraph fully answers the classic question, and more importantly shows you understand how the processes cooperate. Memory to disk, durability, recovery, cleanup. Practice saying it out loud a few times. Let's see them for real. Every running background process shows up in the data dictionary. Query $BGPROCESS, filtering where the process address isn't 0, and you get the crew that's actually running. There's DBW0, LGWR, CKPT, SMON, PMON, exactly the names we just learned. $process gives you the operating system level view of those processes, and $session shows the user sessions connected on top. So the background processes and the user sessions are all visible and countable. We formally tour these dynamic views in Chapter 17, but this is a great sanity check. Anytime you want to confirm the instance is healthy and the whole crew clocked in, let's lock it in. DBWN writes dirty blocks to the data files in the background and in batches. LGWR writes redo at commit, that's the durability guarantee. CKPT records checkpoints. SMON performs instance recovery on startup, and PMON cleans up failed sessions. ARCn archives filled redo logs, but only when you're in archivalog mode. And the trap to have ready, what makes a commit durable? LGWR writing the redo to disk before the commit returns. Next chapter we watch this whole crew come to life in order, because starting a database isn't one action, it happens in 3 distinct stages, and each one maps beautifully onto the architecture. That's Chapter 5, Startup and Shutdown.